All right, so here's the new problem. We're going to take a circle, 4-inch radius, and we're going to cut out a sector with an arc length of x. And it's drawn on the screen in front of you. And what we are going to do with this is we are going to form a cone. We're going to fold these two sides down, these two radii down to meet. So you'll notice that the length of the outside of the cone is the radius of the circle, which is 4. The cone itself, if you look down at my drawing, has a radius r and a height h. And our goal is to maximize the volume of the cone. So a few things that we're going to need to know here. Thing one, well, we've drawn a picture. We've seen this arc that we're taking out here. My stylus has quit writing, so give me a second to reset it. Here we go. Draw pictures and label parts that are important. Okay, I did that prior to you coming in. Introduce a variable. Well, we've already done that. X is the variable, what we're going to cut out. Using that variable, write a function whose extreme value gives the information sought. This is often the trickiest part. And the reason I am doing this fairly complicated problem is because I want you to see the various ways to work through this. But one thing we know about the volume of a cone is that it's 1/3 pi r squared h. Notice that v is a function of the radius and the height, but we've defined our variable as x. And so what we want to do is try to figure out how to turn this into a single variable. And there are a variety of ways to do this. And let's take a look at some more relationships before we get there. So I'm going to go back to the cone, the picture of the cone that I've drawn. And this is something that you're going to see that's going to be fairly common, is that when you're dealing with cones, you can almost always, and when I say almost always, I actually mean always, write the height and the radius using a right triangle. H squared plus r squared is equal to 4 squared. So what we immediately notice is that we can write volume as a function of just the radius. Since the height is equal to the square root of 16 minus r squared, we can now write volume as a function of radius, which is r squared times the square root of 16 minus r squared. And I'm going to say that our problem just got twice as easy. We've got one variable instead of two variables. So we want to maximize. What we could do at this point is we could say, well, let's just maximize in terms of the radius, and then we'll figure out the rest later. But it might be worthwhile to go ahead and look at the circle a little bit before we get too much further. So let's think about this. What do we know about the circumference of this cone? So let's talk about circumference of my cone. Well, I'm going to call this diagram 1 and diagram 2. From diagram 2, I know that the circumference is equal to 2 times pi times whatever my radius is. Fairly straightforward, easy enough. Well, now let's go and look at diagram 2, because the circumference of my cone is the major arc AC. It's the length of that major arc. Let me show you again. Here's my major arc AC. Remember, major arc is the long way around the circle. Minor arc is the short way around the circle. And when I turn this into a cone, oh, look at that. There's the circumference of my cone. Well, how long is that major arc? Well, the full circumference is 2 pi times the radius, and the major arc is the full circumference minus the cutout. So the circumference is equal to 8 pi minus x, but that's equal to 2 pi times r, which means that we can now write the radius in terms of x, which is 8 pi minus x over 2 pi, which is 4 minus 1 over 2 pi x. We now have a choice. We could rewrite volume as a function of x, which is 1/3 pi times 4 minus 1 over 2 pi x all squared times the square root of 16 minus 4 minus 1 over 2 pi x squared. It's fairly complicated looking, but we could find the derivative of that. Or we could say that the derivative of this with respect to x is the derivative with respect to r times the derivative of r with respect to x, which might actually be significantly easier because the derivative of r with respect to x is very straightforward, -1 over 2 pi. I'm going to suggest that that one is easier than that one. So let's take a look. What does that look like? All right, I need my equation again. What was my equation? V of r is equal to 1/3 pi r squared times 16 minus r squared to the 1/2. Notice I've rewritten it without the square root, without the radical symbol to make life easier. The derivative of v with respect to r equals, well, 1/3 pi is a constant. I've got u and I've got v. So let's very quickly find the derivative of u with respect to r. That's just 2r. The derivative of v with respect to r, a little more complicated. So the -1/2 times -2r, which simplifies down to, let's see, the 2's will reduce, -r over the square root of 16 minus r squared. So product rule says u dv, so that's negative, I'll write it out long, r squared times -r over the square root of 16 minus r squared, plus v du, so that's the square root of 16 minus r squared times 2r. To be working again, remembering the derivative of v with respect to x is equal to the derivative of v with respect to r times the derivative of r with respect to x. Chain rule. The derivative of v with respect to x is, I'll do some simplifying. I've got 1/3 pi, or pi over 3, times -r cubed over the square root of 16 minus r squared, plus 2r times the square root of 16 minus r squared, times the derivative of r with respect to x, and looking back, I see that that's just -1 over 2 pi. So I want to maximize volume, critical points and endpoints. Obviously, my endpoints are when x equals 0 and x equals 2 pi, which, of course, presumably will be the same thing, which is, I got nothing. My critical points, I want to set this whole thing equal to 0, which means that I just need to set the part in the parentheses equal to 0. And what I get here is I get that negative r cubed over square root of 16 minus r squared plus 2r square root 16 minus r squared is equal to 0. Excuse me. Let's do a little bit of algebra here. So I'm going to copy this over to the next page. Do I need to? Yeah. Negative r cubed over square root of 16 minus r squared plus 2r times the square root of 16 minus r squared equals 0. Checking back to make sure I did it right. Good. I'm going to multiply everything by the square root of 16 minus r squared. And I'm going to move the negative term to the other side. So what I get here is that 2r times 16 minus r squared is equal to r cubed. Not sure yet whether that was the best thing to do, but playing it by ear, we've got 32r minus 2r cubed equals r cubed. Clearly, I can see that I probably need to bring my r cubed back. 32r, I will subtract it from both sides, minus 3r cubed is equal to 0. Factor out an r, and I get 32 minus 3r squared is equal to 0, which means that the radius is 0 or plus or minus the square root of 32 thirds. Now, obviously, a radius of 0 is not going to maximize my volume. I can't have a negative radius, which means that the correct answer is that the maximum volume will occur when the radius of my cone is the square root of 32 thirds. So that's not really what I was asked. I was asked what length x, but I know that going back and looking at my equations, I had an equation relating radius and, going way back, radius and arc length right here, down in the bottom of my screen here. So I could plug that r in, see, 4 minus 1 over 2 pi x equals 4 minus 1 over 2, whoops, equals 4 minus 1 over 2 pi x, and subtract 4 from both sides, multiply by negative 2 pi, and I would have myself an answer. Let's make sure this answer makes sense. So I'm playing with my calculator here. Should have done this in advance, but I couldn't tell you why. Minus 4 times negative 2 times pi gives me x equal to 28.399 units. Now, question is, does that make sense? Circumference of the original circle was 2 times pi times 4. 8 pi, 8 times pi is 25.133. So we're cutting out more than the original circle, so this makes absolutely no sense. And so therefore we will throw away this whole video and start again another. All right, so I've just made a new little video and I'm going to paste this on the end. So to you, it will seem as though I was there. And then I just suddenly changed clothes and then I was back again. So I went back and I redid this problem and oh my gosh, do I feel like an idiot. Here's what I typed in my calculator. The square root of 32 over 3 minus 4 times negative 2 pi. And that's how I got the number 28.399. You're probably already saying, Mr. Armerding, you spent months, weeks, years telling us, don't forget order of operations when you type stuff into your calculator. And sure enough, I forgot order of operations when I typed stuff into my calculator. And so redoing this, we actually get that x is approximately 4.612 units. And so what we want to do is cut out approximately 4.5 units out of the edge of our circle. Remember, the question was, how big should this arc right here be to maximize the volume of the cone? And the correct answer is it should be 4.6. Well, in this case, our units are actually inches. So it should be 4.6 inches long. So I'm going to try to append this 30-second video to the end of the previous video. And I just thought that was, I don't know, worth not making the whole video again and worth having a good laugh at myself for being an idiot. All right. Thanks for watching. I hope you learned something.